one example of initial numerical example. If we consider a spring mass system as shown in figure 1.3 with a mass of 10 kg and spring stiffness 100 Newton per mm, if the given mass, give the mass a deflection of 20 mm, then release it, that is set in motion, we would observe the system oscillating as shown in figure 1.3. That means what? Here, this is the system. This spring is 100 Newton per meter, then this is the mass 10 kg. If we deflect it by 20 mm and leave it, then it will start oscillating. 20 mm it's getting displaced, then it will come to here, then it will go up, it will come like that, it will start oscillate. This is how they are explaining. To reach a deflection of 20 mm just applied, we had to apply a force of 2 Newton. That means like this is 100 Newton per meter, right? So 20 mm means just 2 Newton if you apply also, it will move 20 mm because spring stiffness is 100 Newton per meter. So as noted previously, the rate at which the load is applied will have an effect of dynamics of the system. Then what does it mean, right? Like how we are going to apply the load, rate of load. We will suddenly pull it and proceed, pull it and leave it, or we will gradually pull it. Depends on that rate of loading. It has effect on the dynamics of the system. Would you expect the system to behave the same in the following cases? Let us examine, like for example, if 2 Newton weight is dropped onto the mass from a very small height. This is the mass, for example, some bucket, weightless bucket. If you are just dropping it, how the system will behave? Or if we put that 2 kilograms of sand was slowly added to a weightless bucket and attached to the mass. Slowly if we add it, how it would behave? So it will not behave the same way. Assuming the linear increase of the load to the 2 Newton load that over the periods of 1, 3, 5, 10 seconds. That means within 1 second we are applying 2 Newton, or we are taking 3 seconds to apply the 2 Newton, or we are taking 5 seconds to apply the 2 Newton. So based on these different rate of loading, how the deflections will vary, we will see in the figure 1.4. For example, here at the start of the second, 0 second, nothing is there. If we leave the load within 1 second, then it will start oscillating like this. 1 second, this dotted line here, you can see it. And this graph, that is a 3 second one. The next one is a 5 second one. Then next one is this dark one is the 10 second. So remembering that the period of vibration of the system is 2 seconds. These systems, the natural period is 2 seconds, 1.987 seconds, because frequency is k square root of k by m, right? So k is 100 Newton meter, 10 is a kg, so we can 0.503 seconds. It's a frequency. Then period is 1 by frequency, the 1.987 seconds it's coming. So this system has a period of 1.987 seconds. Okay. So remembering this one, this is just a so in 2 seconds. We can see that when the load is applied faster than the period of system, if you are applying the load, that is within 1 second you are applying the load faster than the period of the system, then large dynamic effects occur. See, you can see these large dynamic effects occur. Stated another way, when the frequency of loading 1, 0.3, 0.2, 0.1, our sample loading is close to 0, is close to or above the natural frequency of the system, we can see the dynamic effects are large. If the above the natural frequency, that means frequency is more than 0.5 hertz in our case, dynamic effects are large. Conversely, when the frequency of the loading is less than the natural period of the system, little dynamic effects are noticed, most clearly seen in the 10 seconds ramp up load. For example, 0.1 hertz means this dynamic effect is very less. Okay, so rate of loading matters a lot for the dynamics of the system. This is what we try to explain here in this example.